Hello friends, welcome to follow up. In this video, let's have a look at problem 2707, extra characters in a string. So for this video, I'm going to explain a solution based on dynamic programming. So here we are going to look at two formats. So in the first format, we're going to use tabulation. So this is to fix the idea. And in the second format, we're going to use recursion, but both are in the line of idea, that is dynamic programming. So here we are given a zero index string S and a dictionary of words called dictionary. So we have to break S into one or more non-overlapping substrings such that each substring is present in dictionary. There may be some extra characters in S which are not present in any of the substrings. So we are required to return the minimum number of extra characters left over if we break up S optimally. So here we have two examples. In the first example, if we look at the dictionary, so we have leet, we have code. So if we break the leet's code into leet, S, and code, so we have X left over. So the output is 1 for this problem. And in example 2, so we have hello world, right? So we have hello world. So if we break the S into C, hello, and word, so we are going to left over C. So we return 3 for this example. So before we do the coding, let's also look at the constraints. So here the string has a very a small length that is bounded above by 50, as a dictionary dictionary elements are also bounded above by 50. So in this problem, notice that dictionary is given in the form of a list, right? List of strings. So here dictionary I, in other words, the generic element in the dictionary, and S consists of only lowercase English letters. So here dictionary contains distinct words. So actually this is like a set, right? Plays effectively a role of set. So with that said, basically we are ready to do the analysis and the coding. So here I'm going to do dynamic programming. So I'm going to do two formats, right? So the first one is tabulation. So for this is used to fix the idea, right? And the second one is basically write in a recursion format. So this can be regarded as a little bit optimization. So now let's first look at format 1. So here let me add some annotations. So first I want to define a DPI. So this is the generic element for the tabulation. So this basically I would like to interpret as the mean or minimal extra characters if we break S up to this index, right? So here I'm writing ending at I+1. In other words, this here it contains I character, contains character from index 0 up to index I and including, right? That's why we write I+1 here. So this way, actually, it's easier to understand for the idea. But for coding, if you change or manipulate the index a little bit, you can write slightly shorter code. So with that done, basically, we are going to do the coding. First, we initialize length. That's the S. So here I changed this dictionary name to be D, just for the convenience of writing. Another thing is that here D essentially plays a role of set, so I can make D a set. Right? This actually might accelerate the membership check later we are going to use. So now first let me maybe just write with some redundancy. So if n equals 1, so we just need to check if the character is inside the set D or not. If so, there's no extra character left, so we're going to return 0. Otherwise, we return 1. So let me write in this format. If S in D, so we return 0. Otherwise, we return 1 because we just have 1 character in total, right? So next, if n is larger than 1, so we are going to use dp. So first we make a dp table of length m. So here n is the same as length s. So sometimes, as we mentioned above, so if you manipulate the indexing, and then you initialize a dp table of size m plus 1 and adjust the dp interpretation, you can write slightly shortcode. But here our purpose is to fix the idea, so we write with some redundancy. So let's first set dp0. So dp0 is determined by if this s0 in D or not, right? So if it's in D, so we are going to get 0, right? If it's not in D, so this is going to give us 0, so we set it to be 1. Now let's iterate. So this basically for I in range from 1 to n, right? We want to set dpi for each index from 1 to n minus 1. Then for this, we need to check the previous strings. So we check for j in range. So I, so we start from I. Let's see, -1, -1. And then we are going to consider this substring, that is s, from j and ending at index I. So we write I plus 1, right? So the temp has a length, that is start index, that is j, end index is I, so it's I minus j plus 1, that's the length. Or you can regard it like this, so the I plus 1, this index minus this one, right? So here j, so minus j. So mathematically they are the same, but they have a slightly different thought process, right? Then we are going to check if temp in D, right? Then it means that from index j and ending at index I, so this is the valid word in the dictionary, right? Then let's consider this case. If j is greater than 0, so we can set dpi. So here we cannot set it to be 0. We can set it to be a very large number. Let's see. We can use float infinity, or you can use, so because the length is 50 at most, you can use, for example, 51 here. That's also good. So you can use 51. So dpi will be the mean of dp j minus 1, right? So ending at index j minus 1, what's the minimal extra characters? Because starting from j and ending at I, so we don't need extra characters. So this is this one, so we need to take the minimal of this one. So this is the case. Another case is if j is 0, right? In this case, so we can set dpi to be 0. The reason is that starting from index 0 and ending at index I, so it's as a substring or word, it's in D, so we have no extra character left. Or you can just use I minus I, so you use this formula, but it's actually it's inconsistency. So this is the one. Another one is that if this temp is not in D. So in this case, so let's consider again if j greater than 0, right? So in this case, we need to do this. So we need to mean, so we want to take minimal of dpi and then dp j minus 1. But from index j up to index I, we cannot, we should regard these characters as extra characters. So the total count is I minus j plus 1, right? So this is exactly the comment here. Otherwise, if j is less than 0, so dpi will be mean dpi. This dpi, you can understand it as its previous state. Then from index 0 up to index I, so all are extra characters. So we write I plus 1 here. So overall, afterwards, we just need to return dp n minus 1 because it's the largest index, or dp negative 1. So this way, so we finished one solution for this problem. So let's first do a check before we make comments. It passes the first example. Now let's look at the generic test case. Yeah, it passes all the generic cases. So here for this format of solution, so it's very verbose, but here our purpose is to fix the idea. First, so if we adjust the interpretation of this dpi, so we can avoid to do this check g greater than 0. So g greater than 0, right? So this saves several lines of coding. So this is the one thing. Another improvement, maybe we can write using recursion. So here what we do is that, so we want to check the minimal extra characters if we ending at certain index. So here we are ending at index I, right? So we can do the other direction. So we can consider the dpi as the mean extra characters if we start from index I and onwards, right? So let's write the similar thing. So you can, so here you can use this new interpretation, write a format like this. That's totally fine. Or we can also write using recursion. So here for the second format, I'm not going to repeat or modify the code here, because this is actually very routine. If you change the interpretation of dpi to be mean extra characters if we break s from index I onwards, so you can write a similar solution as v1, right? Now let's use somewhat this interpretation, and we write a recursive solution, right? So here first, again, so I'm going to use this part. And so d equals set d. So make this dictionary is set, right? So because here the dictionary, so though we call it dictionary, it's a list, right? And then we get the length of this s. And next, what we are going to do, we write a utility function. Let's call it dfs, maybe. It's just essentially a traversal. So here, dfsi is this interpretation. So from if we mean extra characters, number of extra characters. So if we break s from I onwards, right? So for this, first, here I is interpreted as the index, right? So if I equals n, in other words, it's larger than the largest index n minus 1. So this will return 0. So this can be regarded also as a stop condition or base case. And next, we are going to set a float number, that is infinity. So here, this is in parallel to the first version. But if you look at the constraint and you notice that the length of s is 50, bounded by above by 50, you can set this to be, say, 51. That's also okay. Next, what we want to do is that we want to look at the index after I. So we can see for g in range I plus 1 up to n plus 1. So notice here we're writing n plus 1 because we want to subtract a string. So here the substring, what we are going to look at actually is s, I, and g, right? And then we want to update this result. This result will be mean of result. Then what we are going to do, let's see, we look at dfs g, right? So from g onwards, how many? What's the minimal extra characters if we break S, G, and onwards, right? And then we want to check this one. So what's the contribution of S from I to index G, right? So here the thing is like this. The index is I, right? And then you up to G, and then you onwards. So here is this DFSG is this part, and then we want to check the extra characters contributed from for the substring S, starting from I and ending before index G, right? So this is actually 0 if S I up to G is in the dictionary. Otherwise, so we need to count all these characters as extra. So that the ending index is G minus 1. So starting index is I. So it's G minus 1 minus I plus 1. Right? In other words, G minus I. So this way we finished updating the result. Now we just return this one. And afterwards, after we finish this utility function, so we can call this. So here we can use cache. So just for accelerate. So now let's return DFS. So we should start from index 0. So this is the second solution format. So I would say the idea is quite similar to version V1, but we use slightly different interpretation. We follow this interpretation, and then we wrote in a recursion format. So now let's test this case. So we have changed this to be V1. Now we can directly check this. So was never closed. I see. Let's see. We need to add one more. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So with that said, that's basically about it for this specific problem. So this problem provides us a good instance for practicing dynamic programming. So in this video, we shared two formats. The first one is standard tabulation. So we use this one to fix the idea. Actually, this first version is very verbose. It's like translating our thought from English to coding format. And the second one, and maybe we need some thought or design to make the code more neat or shorter. So with that said, that's it for this video. Thank you.